Okay, welcome. So today we are honored to welcome Rebekah Bogdanoff, community lead of Duality AI, which was co-founded by fellow Angie Pura Shah. Duality AI focuses on using digital twin simulations to solve real-world problems and create safe, predictable, and resilient smart solutions. So Rebekah earned her master's degree from our Department of Visualization, now part of the Performance Visualization of Fine Arts. And during her time at the Texas A&M, she collaborated with the Oceanography Department to create an ocean chemistry educational video game. She also worked with Gearbox Games to develop graphics curriculum for the classroom. So in her current role, Rebekah creates simulations for AI training and works with schools, organizations, and online communities, interested in Duality's free EDU tiers of simulation software. She helps learners and educators master the simulation techniques to bridge the gap between virtual training and real-world applications. So with that, please join me to welcoming Rebekah. Thank you.
Okay. Glad to be here. So I'm Rebekah Bogdanoff. I graduated a couple years ago from here, and I'm really excited that I get to come and give this talk. We're going to be going over one of the processes that led to this paper that was award-winning last year. So fine-tuning YOLO VA for accurate unmanned aerial vehicle detection with digital twin simulation. YOLO VA is just a popular open source model. So if you're familiar with model training, you usually start with like large base trained models, and then you build upon it to have specialized purposes. Unmanned aerial vehicles is a fancy way of saying drones. As you can see in the picture, that would be a drone. And then we use digital twin simulation to create data that we can then train the model that works in the real world. Feel free to raise your hand and ask questions during the presentation. I like a more engaging presentation if you want. There will also be time for questions. Okay, so who worked on this project? It was our company, Duality AI. We built Falcon. It's a digital twin simulation platform that's used for training and testing AI models. And then it's built on Unreal. So if you are familiar with Unreal and you open up Falcon, it looks very similar. We specialize in creating the high fidelity data that is proven to fill in the data gaps, and then also gaps for like complex and dynamic scenarios. This means that we can create data for situations that maybe are more edge case, maybe for situations that are more difficult to gather data, or for situations that just have like less data, but you need more because you need a lot of data to train a model. So we found that digital twin simulation is a good application for filling in those gaps. And for this, we worked with the XM30 Advanced Capabilities team of the Army. They lead innovation for the U.S. Army's XM30 combat vehicle, and they want to improve battlefield readiness, lethality, and survivability through the next-gen tech. So really looking at where all this technology is going and how can we kind of keep up with all of that. This is a quote from them. So they said, at 8 months into our CUS program, or Controlled Unmanned Aerial System Program, by leveraging Falcon synthetic data, we've already seen double-digit improvements in the MAP50 accuracy as validated against real data. What this means, MAP50, if you're unfamiliar, is a metric for measuring how well the model is performing and being able to accurately annotate and understand the real-world data. Double-digit improvements is very good. Especially for real-world application. It's not quite percentages, but it's a similar, you can think of it similarly. 1 would be the best score, 0 would be the worst score. So double-digit would be like jumping from 0.6 to 0.8, which is a drastic improvement. And being able to do that after 8 months, after they've been working on improving it for 8 months, is a real testament to how well this can supplement areas that the real-world data just can't do. So if you guys have been keeping up with the news and noticed that drone warfare is a big part of like military news right now, especially if you've kept up with anything in Ukraine, they're used for recon, target acquisition, precision strikes, because they're fast, they're cheap, you can do a lot of them quickly, and they're kind of difficult to detect, which is something that we'll talk about later. Definitely you can imagine how it would be more difficult to detect a drone versus a big old airplane. A lot more flexible in its maneuverability and a lot smaller and difficult to see. Additionally, it's always changing. So it's rapidly developing. You need systems that can keep up with the weapon development. So the existing detection systems can't really keep up. And that's one of the reasons that the Army was working with us, is to develop systems that can keep up with the real world technology. Well, it's all real world. Keep detection systems up to date with the systems they're trying to detect. Felipe, also feel free to jump in at any time if you have interesting things to add. So the challenge is the data bottleneck. Again, if you train any AI, you know that they have to have lots of data. That's a huge talk right now, just for any AI right now. It's a big thing about data domain. And the truth is that these systems can detect drones. AI can be detecting drones in the sensors and say, this is a drone, it's not a bird, and track them as they move. So they can do that with high accuracy if they have the right data. But there's problems in getting that data. And you can see this is one of the before images. The top one is a drone. That's correct. It's 0.8%, or not percent, but it has an MAPPD of 0.8. Pretty confident that it's a drone. But it's also 0.6 confident that that light is a drone. So not 100% accurate. Information-rich real-world data is important to have, and that can be difficult. Yes, Professor Zhao.
So are you able to detect different kind of drones?
Yes.
So basically you can have 5 categories of drones instead of drone or not drone.
Yep, that is also something we will get into. So not only, I think that would tie also into the information rich and tie into the quick development of the tools. Like they can easily develop new types of drones, and then you have to train for those types of drones, but getting access and images to train for that drone could be difficult, especially to do it rapidly. And it could be dangerous if you don't have access to it besides real world applications. They might not have the variability that you need. So if you have a lot of pictures of a drone, just a drone in the clouds, in the sky, with no trees, no lights, that doesn't have the variability you need for real world application. In order to trick the model, the drone would just have to fly near trees. And all of a sudden the model would have difficulty detecting it. So there's a lot of difficulties in obtaining the type of data that's needed to train it well, obtain it quickly, and do it in a way that's still accurate and cost-effective if possible. So this is where simulation comes in. So Falcon is the digital twin simulator. It's modular, photorealistic. You guys have seen Unreal. It can get very hyper-realistic. And that's one of the reasons that our founders decided to build this on Unreal, is because it's good and just keeps getting better. So you can put together different drone models, UAVs, and different environments to simulate data for the different drone types, not only different environments, but also different environmental conditions, rain, sun. If you need more, let's say, rain photos, you don't have to wait until the weather turns rainy in the right location and then transport everything there and take the right images. And then if you go back to the lab and decide, oh, we didn't do it right, you have to wait again. You don't have to do that with synthetic data. You can just queue it up, get the weather going, collect the data. If you need to change something, queue it up again, change the thing, generate 2,000 more images. We have all the sensors, so digital twins of different sensors. You guys are familiar with rays within Unreal or materials. Those can all be used to mimic the sensor output of real world data. So infrared IR, you can have materials that contain heat information, and that can be read by a digital twin IR sensor. All of a sudden you have infrared data. You have to build the twins, but once you have it, it's easier to iterate through and train the process. And especially with AI, there's a lot of balancing and figuring out what you need to have in order to get the output that you want, and being able to quickly iterate through that and work through that process flexibly and cheaply is a good thing for simulation. Also, again, if you guys have trained data at all, especially with these vision systems, you can see the top, there's a box around the drone. With real world images, you start with a picture of a drone, and then someone just goes in and draws a picture or a box around the drone and says, this is a drone. If you have 5,000 images, they have people, their whole job is just drawing boxes around things. But with simulation, it comes automatically because you're just recording where the pixels are, you draw the box around that. So automatically labeled, And again, if you need to iterate through it, the labels just come with it. You don't have to label like 6,000 images again. Rapidly customizable, so you can change things, and then ready for model training and validation. The data just comes out ready to go, and then you can feed it into a model. The real question and the real sticking point for some of like potential customers or people who might want or not want to use synthetic data is, how do you know that it's accurate to the real world? Because if you train a model in simulation, it works fine in simulation, but doesn't work fine in the real world, that's useless. So we call that bridging the sim to real gap. You need to have it to where the simulation is indistinguishable to the model from the real world. You might be able to see a difference in the data. You might be able to look at two images and say they're different, but you're not an AI model as much as they're anthropomorphized now. We just need them to look at it and not see a difference. And if they don't see a difference, then we know that the training that works in the simulation will be able to translate into the real world. Because in the AI's quote unquote mind, it's the same. So we have a system called the indistinguishability score. It uses Dino V2 embeddings to measure realism at the feature level. Felipe, this is where you can jump in if you need, because he's our AI guy. But basically, the Dino V2 will look at the data sets and will find features and kind of quantify or qualify those features and then plot those. I'll show it in the next slide. I'll talk more about that. But basically, if the plot will tell us whether the model, the Dino V2, sees the images as two separate data sets or whether they're indistinguishable. It can't tell whether the image is from data set 1 or data set 2. Layman's term, it can't tell if it's synthetic or real. Yes.
So another method people are using nowadays, using virtual large language model, VLM. I'm not sure if you guys have started using that, because with all the visual component of large models, what people call foundation models, you can directly upload the image, how it to evaluate it based on the realistic. It give you a score, but again, it's only depending on the model you're using. But that's what people are trying to do. Probably.
Yeah, Felipe, have you heard of that? And you know,
Can you, because the microphone, could you repeat the question kind of? Was it VLMs or?
I'm mentioning about a virtual LM. Yes, it's a VLM that people are using to evaluate the quality of the generated images. And you can probably ask the LM to give you a score, and you can compare different input. And that's probably one way to explore. I'm not saying that's the right way to do it, but it seems to be that, those VLM models are getting better and better. It seems to be a reasonable solution for this kind of problem.
Yeah, we haven't tried that exactly. I think we've we've done like out of curiosity, like used some of the VLM models and gone like, okay, does this look real or synthetic? So I think they do a good job overall, but we haven't. So we have submitted some and gone like, oh, okay, is this real and synthetic? And they have, in a couple of examples, have gone like, correctly said like, oh, this looks like a video game rendering versus like this looks like a real image. But we haven't explicitly used it for something like this. I think Dino V2 being kind of a foundation model has a lot of similarities in that, but definitely would be interesting to sort of compare the two.
I'm wondering too, Felipe, if one of the reasons we haven't looked to it as much is because we really need it to align with a specific data set that would be representational of the real world. And some like VLMs are more looking at just like general, is it realistic? Correct me if I'm wrong.
Yeah, that's a good point. Definitely.
Okay. Yeah. But things are moving fast. We might in the future.
Yeah.
So one of the things this can also do is it says predictive tuning of quality for the model training. So basically, before you go through the whole training process, you can see, okay, is this going to be indistinguishable to the model? Are the results going to be what I want it to? So this is like a visual representation of that. You can see at the top would be the real world, the bottom would be the synthetic images, and it goes through the process of embedding and dimensionality reduction. And then the scatter plot would be like 2D representation of what the model is seeing. You can see in the final one where it says nearest neighbor analysis, where the pink and the green dots are all scattered in with each other. That says that they see it, the model sees it as like the same data set. They don't see any different. If there were a difference at the model phase, you would kind of see more like what you see at the, I'll move over. You'd see more like this on the plot, where one group of green, one group of purple, and that is saying that the model thinks that this is two separate data sets, versus this one is like, it's all one, it's all overlapping. Yes.
Have you checked these scores against when you have a swarm of drones?
Have we checked this score against the swarm of drones? Felipe, do you know if we worked with drone swarms for this specific project at all, or just the single one?
Yeah, no, we didn't do swarm of drones. I'm kind of curious the question, like, so you mean like how like what's the indistinguishability when we have a synthetic swarm versus a real swarm, or
Yes.
is it just like individual versus swarm?
Yes.
Yeah, the problem is that our military people overseas, they have the problem that they have a swarm of drones and they don't know which one is the lethal one. Then their algorithms try to identify which ones are the one that they have to destroy.
Yes.
Supposedly, that emits some radiation totally different than the other ones. That's why I am asking if you distinguish the swarm, and on that cloud, if you see something different with one of them.
Yes.
This is my question.
Yes.
Yeah, that's really interesting. Yeah, we didn't do swarms. I think that's kind of like a next step, but I think it's definitely something where like synthetic data can really like help in. We saw it because it starts becoming more of a, not just like, is this a drone, but like what type of, more of a classification task, where it's like, what type of drone? Is this a like non-leader drone versus a leader drone? And that's really where synthetic data starts to shine, because you can sort of plug and play and swap, like, oh, the leader now looks like this, so now we're going to make data like this. Oh, the leader now changed and it looks like this. So that's something that I think would be very interesting. But for this phase, we didn't do swarms.
Yeah, real fast. We one of the great things about the like Falcon as a platform is it has a lot of flexibility. So people are saying like we could do that. Some of it depends on just, what our customers need. So if they came to us and said, can you do this? Yeah, I'm not sure what the sensor would be for that, but I'm assuming that we have one that would work or be able to develop one. So that's, I don't know, that's a really interesting use case for sure. We just didn't get paid for that, but it could definitely work. Oh, we have a question over here and then I'll come back to you. Yes.
Yeah, so I like the use of the PCA, but I don't know if it brings down the 2D embeddings to too much of a dimensionally reduction. So what I mean is, when I try to do this embeddings and I use PCA or SVD or bring it down, so I'm reducing the model, sometimes I see this correlations, but when you go back into the bigger dimensional vectors, they're not correlated. So I don't know if there's a way to do this matching so that you can prove both of the data sets are correct or like similar to each other using cosine similarity or vector product.
Did you hear that?
Yeah,
okay?
yeah, definitely. So for the most part, so we've explored like PCA, dimensionality reduction, t-SNE, and UMAPs. Definitely, UMAPs and t-SNE have like maintain more like information, kind of more of that information as they go down. But we've seen that PCAs tend to capture enough information. So kind of the full story, like for indistinguishability, is that we get this indistinguishability that tells us like, okay, is the data, does it look realistic enough? And it gives us a value between 0 and 1. And we've done this a few times, that we've seen the relationship between kind of any sort of between a performance difference when you use this data, when you evaluate it, how does that performance differentiate when you train a model on real data, when you train on synthetic data. That has been correlated with this indistinguishability score pretty well using the PCA. There's definitely some use cases where keeping some of that higher dimensionality information and doing UMaps, t-SNE helps. And keeping the entire embeddings and doing cosine similarity, the embedding space is just very large, and so there's not as much information. So that's why we kind of avoid the full embedding. But definitely UMaps and t-SNE we've used sometimes, but PCA tends to be our main go-to as like a first step.
Mr. I just thought of this too. Would you mind looking, are you still on the Zoom?
Yes.
Would you mind seeing if there's any comments as well? I don't want to forget thank you. Felipe, you as well, if you could look and see. I think between the two, we'll be able to catch them.
Yeah, I think someone has a question in the Zoom.
Oh, okay.
You can ask John, use himself to ask directly. That's actually fine.
John, you want to unmute and ask? Thanks for joining, by the way.
Hello, can I speak?
Yeah, we can hear you.
Yes.
Okay. So a question I have is, because of connectivity, I missed a part of this presentation. But when you're talking about drones, are you talking about like things like quadcopters, hexcopters, or are you talking about fixed wing drones as well?
Yeah, mainly quadcopters.
Okay. Yeah, because those have a specific form factor, and they tend to move much slower than, let's say, fixed wing drones that are used in combat environments, and so probably a little bit of a different ball game than those. So okay, that's my question. Thank you.
So my question, again, getting back to the simulator side, we are trying to work with a professor from ECE to see if we can simulate the radio signature of individual drones. So in your simulation environment, I'm not sure if you guys are considering like expanding for example, not just a visual, probably you're already doing audio or whatever. At least I was doing audio related signals. But are you guys going to add some extra data modality into the simulator, or what's the current plan in your Falcon environment?
Yeah. What would be the sensors? Yeah, go ahead.
Yeah.
I was just gonna say, I think there's definitely a few sensor modalities. Rebekah, do you have that video that has the different sensors? At least, or I think it was a couple slides maybe, but I'm not sure. Okay.
Let me I can see if I can pull it up and send it over.
I think it's fine. Just go ahead with the slides. We can talk about that.
Yeah, at the end we'll look at it.
Okay.
But yeah, we have a full sensor suite. And again, it's one of those things where it's like, if we have a specific customer that's wanting the sensor that we don't have in the suite, then we work on developing it. So we're definitely going where we get development where we can get the funding.
Yeah, and so for example, IR is an example of that. So we didn't have IR sensors, and then we worked with customers to develop that. SAR, I think, was a similar case where we worked with customers that wanted SAR sensors. And I think there's other types of sensors that we've kind of developed. I'm not sure about radio frequencies, but I'm sure that would be something we could definitely work with a customer to develop.
Like an SDF or something, I imagine would be similar. Yeah. So yeah, great question. Any other ones here or in the chat before we move forward? Great, appreciate the engagement. So this is the question: can synthetic data fill the real world gaps? We had the two detection variables, or basically two of the gaps that they were trying to fill. One was smaller drones, they're harder to detect. They weren't very represented in the data. It makes sense, right? Something smaller, there's less pixels on target, or there's less pixels represented by that object within the test data or the training data. So the model might not have those strategies to identify something that's fewer pixels. So that was one item one variable we were working with, and the other one was environmental clutter. As I said before, something like at the top, the real world training data where it's just a drone against the sky. You can see how that could be different than something at the bottom where it has the lights. And you did see that data or models trained on the top one with no clutter didn't perform well on the ones at the bottom because it had those false positives. So that's why synthetic data in the middle came in. So we generated the data, we trained the model. We trained one just using the synthetic data set. We trained another version of the model on the real data set. And then we evaluate those on a real world data set. It's free to use. It's the IEE Visco. I'm not going to read it all. You guys can see it on the slides. And it has 6 different drone types, 3 different weather conditions. So we were validating it against that to make sure that it jumped the gap. This is the first test with the small drones. So you can see on the left, this is training using the real data set that only had the large drones, didn't have representation in the training of the small drones. And for the data that contained images of the large drones, 0.96, pretty good. So it was able to detect the objects that it was trained on, basically, and the scenarios that it was trained on. But with the small drones, 0.47, that's less than half. That's not a very good score. So when the drones were smaller and you could think farther away, which you can see why that would be more important, or not more important, but important to be able to detect drones farther and farther as far as readiness goes. So that was just with the real data. On the right is the synthetic data that included images of the small drones. So again, we take that real, you can see the purple is just carried over to compare. So again, we saw the 0.47 when evaluated on the small drone images. And then with synthetic data that had the small drones, the score jumped up to 0.69. So there's when we're seeing those double digit increases from under 0.5 to almost 0.7 is pretty good. So that's, yes.
Sorry for.
No, do not apologize. I was kind of like thinking people would ask.
So for larger drones and small drones, this establishment kind of when we talk about scientific research paper, right?
Yes.
Then the small drone probably mean the lower resolution images because the load is small, you cannot carry high resolution 4K camera.
The actual drone would have less pixels, so in that way you might call it resolution. But I think the resolution's the same. Felipe, correct me if I'm wrong.
Yeah.
But it's just like, smaller represented in the data. Does that answer your question? Yes.
So you were mentioning large drones, small drones, but I believe you are considering some fixed distance from which you detect them.
So maybe pixels on target. Yeah, Felipe?
Yeah, the distance isn't fixed. So it's the size of the drone in the image, not the physical size of the drone. So the drone is just kind of flying around. And so it's the same drone, but it can have different size. Hopefully that clarifies that question.
Trying to see if I can find. So for this slide, the top one, I guess would be classified as a larger drone, quote unquote, and the bottom might be a smaller, even though they're the same size in the image, they're small. It's smaller on the bottom, but not in like actual 3D space. Does that clear it up? Yeah. Good question. I don't know if that wording was the most clear, but it is what it is. We got there. Any other questions on this slide?
Yes.
Yes.
Have you tested the spectral resolution on the images?
The spectral resolution?
Yes.
Felipe, do we know that?
I think there was a little bit of variation, but I think for the most part it was like 1080 by 1920.
You're asking great questions. Thank you. The other one was on environmental clutter. So again, on the left, we can see the detection with no clutter, just the drone in the sky, 1.0 perfect score, dramatically dropped when it got more cluttered. And you can see how this would be a problem in real world applications. Like if you need a drone to only be against the sky in order to detect it, like that's not very use case. Dropping it below the tree line is incredibly easy and drones are incredibly maneuverable. This is not good for real world application. And then again, on the right, you can see the improvement when we trained on synthetic data that featured the clutter. So again, the purple carries over. And so compared to the real world images, when it's trained on synthetic, it jumped closer to that 1.0 score. Yes, question.
Is this just a regular convolutional neural network that you're training?
It's a YOLO V8.
It's the architecture of that?
You know, Felipe?
Yeah, I think it's still using convolutional networks.
Yeah, okay, great. So yeah, this is just some images that show you the before and after. So on the left is when the model was trained solely on real world data, and on the right is solely on synthetic data. So you can see that even with just training from the synthetic environment, improvements dramatically and drastically over the two images in being able to detect it positively and not have those false detections. So this is a graph showing, again, the real data. So we have, well, I'll read through it. So again, this is the overall MAP50 performance, 3 different YOLO V8 models trained on different data sets, tested on the same data set. So the purple is using only real images for training, tested on the data set, on the unseen, untrained on data set. The MAP50 final score was 0.8. Trained on only synthetic, it was 0.83, which it did do better on just synthetic. But as we tend to see, the best performance is on a mix of real and synthetic. So one of the things that synthetic does really well, I don't think I have it on the next slide. Yeah, synthetic does really well at addressing gaps in training, edge cases, difficult to gather data, and then also improving a model or modifying it as changes happen over time. And so you can see this here where the real plus the synthetic is what works best, because the synthetic data augmented and allowed it to move beyond just what they were able to capture in the real, but the real also grounds it in reality. Obviously real data is not going to have hallucinations, and it's going to have that just immense amount of informational wealth that you get from real world images. So together they work really well. Yes, any questions on this? So this is my cover of this paper and the findings of this paper. We'll talk about some other features of Falcon and of the company, but I want to open up for any questions specifically about this process. Yes.
So you say that you have 6,800 images, 4,600 so on, but how similar they are? Because on the previous slide, it was like slight movement of the drone.
Mm-hmm.
And like, I would say, how distinct are the scenarios for?
Yeah. So you're saying in this one,
Yeah.
the 9 images are not, or 12 images are not actually that much different from each other.
Yes.
So among the whole test image data set, what is the difference? So this is the tested real world, not the training. And then there's 12,000 images in the data set. Felipe, I haven't looked at this specific testing data set. I know it's an open source one that's used for various, like it's commonly used. It does have, let's see, what did it say? 3 different drone types. What did it say about the, yes. So there's at least,
I think it's, yeah.
6 different.
Yeah, so there's.
And 3 weather conditions.
Yeah, so I think basically, so each drone type had its own like capture, and each weather condition was its own capture. So there's like, I would say like 18 different locations that the data was collected in. And so this is kind of the challenge with real world data, is that like you like spend all this time packing up all your gear, going out to the field, collecting data, and then like you're saying, all you get is a lot of images that look very similar. So that's one of the big challenges that comes with doing real data. So there's definitely the variations of the real world data is definitely something that lacks, and that we're able to fill in by using synthetic data and create some more varied captures using the synthetic data versus real world data, where it's like you spend all this time, you go to the field, and now you have field data, but it's pretty repetitive.
Yeah. If I have time at the end, I'll look up this specific data set, see if we can get some previews. So at least 18 variations for the testing data set. And then what Felipe was talking about for the training is the same thing that you see here of like, it's really easy to break down a recording, a movie MP4 into frames, but you do get a lot of repetition. Versus synthetic data, you can create a lot more variability easily and change it as need be. So that's one of the reasons why it's very, very good for augmenting and supplementing training and making it more robust for the real world. Yeah, what other questions we got for this? Do we have any online?
Yeah, someone raised their hand.
Yeah, hi, I have a question here. If you can go back to maybe 2 slides before, right there. I guess I have 2 questions. First of all, is what is the in order to gain the the double-digit advantage using synthetic data, what is the size comparison of the synthetic data training versus the real data training?
You mean like the size of the training data sets, or you mean like the overall
The
size?
size of this, yes, the size of the synthetic data training
Yes.
versus how much real data you used. And the second question would be, I was just thinking about, what if we mixed real and synthetic when you showed this slide here. So if we apply the real and synthetic to the previous slide, can you, I don't know if you guys did that or not, but yeah, this one, and as well as the one before that, test 1. So could you say something about how that would improve the results, the indistinguishability score? You can say it like in a hand waving manner, but so those are my 2 questions.
Yeah, so we're asking specific data differences between the mix versus only real, only synthetic. Sorry, there were a lot of questions in that. Let's break it down. Your first one, you asked about the number of training images for this.
Right. My first question is, let's say, is the synthetic data size 5 times the real data size in order to achieve that extra 20% increase or double-digit increase, or is it of comparable size? That's my first question.
Felipe,
So
do you know?
I don't know if
Yeah,
I'm making myself clear or not, but that's
for the 2 test cases, I don't remember off the top of my head, but they're definitely comparable. They're mainly meant to be like a test to make sure that our synthetic data is capturing what the model is kind of wants. Like, we mainly want to make sure that is our synthetic data capturing this variable that the model needs and is like starving for it to make sure that it performs well. So they're more meant to be like, okay, like the synthetic data is capturing clutter well. The synthetic data is capturing drone size well and simulating that effectively. The comparison here, like the values are similar. I don't know what the data exactly, but can you go to the next slide? One more.
Okay.
But here for the overall comparison, here we do have the size where the real data is 6,000 plus and the synthetic data is 4,000 plus images.
okay.
I would like to add too, for this specific use case, regardless, I think it's a factor, right, of the comparable training sizes. But one of the points of this use case is that sometimes it is difficult to obtain more data. If this is a drone that's only seen in a specific environment that you don't have access to easily, some of these users are looking for ways to get more data to improve it quicker, easier, safer. And so I think that it is a good point, but I also think that this use case does tie into not only does the synthetic on its own, if we had a one-to-one comparison, work better, but
it's
does it work
interesting.
well enough?
Yeah, now that I take a closer look at the bullets here, it's interesting to see that the synthetic plus real, you have 5,000 images to train, whereas the real only, which appears to be the poorest performance, you have 6,800 images to train. So it's a very interesting result. I'm just saying, why do you think that's the case? that you have fewer data points to train with the synthetic plus real, and yet you were able to achieve a better score with real only.
Yeah, that was one of the things that jumped out at me is the 5,000 is less than even just the real only data. I do think one of the features is optimized, very well optimized. So when you get data to see what's the most effective, Felipe, you can again add more detail to that. But I think there was
definitely. So
some selection on.
So definitely. Sorry.
Yeah, go.
So definitely the kind of the key thing is, and I think it's nice that someone brought it up earlier. The real data is pretty redundant. So I think that definitely plays a big factor into this, where it's like with synthetic data, you're able to like fill in some of those gaps and lacks of understanding and variability. And so it's not always like the more data, the better, but carefully selecting the right data set allows you to like sort of improve. So can you go back one slide? So here, a key part of this is that like the synthetic data we were able to have this understanding that like, oh, the model is struggling to identify, like misidentifying the lights as drones. So we can create more synthetic data with more of those. So it's our synthetic data is more targeted and able to fill in those gaps and improve the model performance.
Okay.
Yeah, one of the things I think because of the specific niche of AI training, one of the things we come across often that doesn't always work with the platform is the idea that like more data is always better. I think that more data is better and you definitely need a lot of data. But for example, I host competitions on Kaggle where we allow users to create the synthetic data and test on the real world images. And it's different in those competitions than the other ones on the site because we're challenging users to think about not just gather as much data as you can, but with synthetic data, it's what's the quality of data, what weaknesses are we addressing, really having a strong hand in creating the data, which leads to better performances. And I think is something that sometimes you don't see as much with just real world data because you understand, okay, it's going to align, but there might be some gaps that you don't think about. And so synthetic data, you have to always think about alignment. You have to always think about where's the gaps. That's like the whole nature of it. So it's a specific niche of like AI training skill. I've just found that that's interesting. That the more is better doesn't always quite work because you could create hundreds of thousands of images in the simulation and it could be useless.
Right. Okay. Thank you.
Great. Bryn.
So like what's your guys' strategy for identifying the gaps? Because I feel like there could be like infinitely many like weird situations that that AI won't be able to recognize properly.
Yeah. Felipe, do you want to handle that?
So I think there's definitely the nice thing with synthetic data is that we can like test any sort of hypothesis that we might have. So for example, like we talk about the key variables being like the drone size and the clutter. Another one that we sort of like thought might be important was the weather conditions. So we're able to like go to synthetic data and like see like, okay, how does weather condition impact the performance of the model? We create a data set that has different weathers, and then we train on just one weather and then see how that performance changes. And what we actually saw was that the weather didn't have an impact. But we were also able to like dive in more deeply and see that like, okay, overall weather doesn't really have an impact, except like when the cloud is the same size as the drone, then you start getting some sort of issues. But you're able to do that with synthetic data through like sort of testing. If we go back, could we go back a couple of slides to like the overall indistinguishability? Yeah, there. The other thing is that you can use kind of the indistinguishability plots to get a better understanding. So this was something that happened with the sort of the street lights, where basically we had these scatter plots and we know so each one of these points represents either a region of the image or the image itself. And so we're able to basically see like, okay, like for the most part, they're kind of indistinguishable, but I see this little cluster over here that's kind of hanging out by itself. And I can then zoom into that cluster and go like, okay, within this cluster, what are the images in here? And so what we saw was that like, oh, a lot of the images in these clusters have these street lights. So that allows us to go back to the drawing board and go like, oh, okay, we should make more synthetic data with streetlights because it seems like it's something that will help our indistinguishability. So those are kind of the two main methods. But yeah, it's kind of definitely a challenge because there's so many variables, but this kind of allows us to ground a little bit and be able to pick out which variable we think is important.
And that's one of the things we saw in my previous talk with Alyssa. She was saying one of the strategies she did to align it was starting with a smaller data set, so there weren't as many variables, and then addressing just what's within that data set, and then scaling up gradually to understand what are the differences. So that was a strategy. So there's lots of different strategies. I wanted to pull up the EDU site. This keeps getting in my way. So this has some lessons, and I should have shown this at the last presentation, but I didn't. And it talks about like how to analyze what might be going wrong. So for this first exercise, you run data, you train, and then I pull up just some of the images that were not categorized correctly. And so looking at this, you can see there's a lot of false positives with, it thought the hand sanitizer was Cheerios. It thought that the toaster was Cheerios. And for the data set, we just had the box of Cheerios within a room. We didn't have any other objects. So looking at this, it tells me I need to train the model not only on what to detect, but what not to detect. There needs to be other items present. There's a misalignment between the two domains. And so then it has you go back and include other digital twins, other consumer packaged goods that are in the data set. And it should be, I don't know if I have the visuals for it. So there's all the consumer packaged goods, and you train it, and then you can see that now it's able to, before it was classifying objects, and then with the clutter. So like Felipe said, there's different strategies, but sometimes it's we can use our human logic and know things that the model doesn't know, because they're really smart, but they're not humans. Yes, another question.
So what are you considering that maybe the fact that, for example, light poles are static and drones can move, the fact that movement is if object is moving, it's more probable to be a drone. So because doing convolutional neural networks, as I understand, you just were training on the snapshots, but what if you add dynamics in it, in the way that if the object is moving in the sky, with a much higher probability it's going to be drone?
Yes. I'll let you answer that one in a second as well. But I'm going to talk about a scenario where we also introduce, I guess they don't move, but clutter objects such as birds and commercial manned airplanes, such as a jet or something that's commercial. So there would still be challenges with that. But Felipe, did you hear the question?
Yeah. So one of the follow-up works after this, we worked on developing a real-world demo that we presented, I forget at what event, but basically where we had a drone flying around and capturing the images in IR. And so there's definitely a lot of strengths in having that sequential data. And so the way we went about it is that we kind of kept it. So we added a tracker to leverage sort of the sequential nature of drones and of the images. And then on top of that, for instead of using 3 channels for YOLO, since we were doing IR, we used 3 sequential images. And so that kind of gave us a really good boost in making and tracking the drone. And it's still a pretty easy and straightforward way to leverage the sequential nature. And yeah, I think you have some examples there.
I'm sorry I didn't put the clip in there, but if you go to the Duality YouTube, we'll have.
I think it's in the middle. You sure?
Was it?
Or that same video.
Yeah. Oh, I'm not seeing it when I'm scrubbing. This is there's a couple variations, and I think this one didn't have the variation that had the VB sets. But follow me on LinkedIn.
Okay.
I'll post it. Sorry about that. But yeah, good question for sure. Let me cover the rest of these slides real fast, and then we will get back to questions. So one of the features that we are introducing is called VibeSim. And so it's a cloud platform where you can use a Gemini agent to help modify the scenario. Right now it's only accessible to pro users or like paying customers. But I'll give you guys a QR code. You can request to access it as EDU users. I'm not gonna lie to you, it's pretty much only the people that came to the talk this weekend and the talk today. So just because we don't have like servers to support everyone. So if you're interested in what you see, you can be doing that. This example though shows how you can create data similar to what was in this example. And then you can test it out on that data set. So this is him placing, you can place markers around that will control where the camera moves to capture the data. This is it sped up. You can see it's capturing lots of images of the drone in an environment. And you can use the Gemini agent that's trained to specifically work with our Falcon scenario to do different variations. I have an example that walks you through the different variations that we know are going to work 100% of the time, because you know that sometimes the agents, they get hallucinations or get confused. So if you do download this, I recommend going through the example and then kind of testing it out. But you can see here we're adding in the planes, adding in bird confusers in order to improve the output. In this specific VibeSim scenario, you can also take the data and run it through a Jupyter notebook, which is basically just like a modular little Python script with cells that you can run. And one of the things it does is do data analytics for distribution. Distribution of like what the size of the drone is in the images. So you can control whether it's a Gaussian distribution, and so you have a good representation of small, large, and medium drones. You can do just a standard where it's flat. One of the interesting features is you can also do custom distribution. So if you wanted to train a specific data set, you can analyze what the distribution is of the pixels representing the drones in that data set, feed that into this, and then replicate that. So if you have a data set that has a lot of large and like 25% small, you could replicate that and then ask Falcon to generate images that match that distribution to better train. So that's a fun one. We also have a couple different example scenarios you can test, and then you can download any of the cloud scenarios that we have freely accessible. So another one of the example scenarios that will pop up is Alyssa's pill one. You can see that with this one, it's pills for pharmaceuticals, and you can work with like pills that are damaged, and you can see down here the YOLO is supposed to be counting how many pills are in the viewport. Right now, because it's too high, it wasn't trained to detect pills at this size. It doesn't work. And again, with this one, you can take the data, you can run it through a Jupyter notebook, feedback the training, and now the model works. So that's a fun little example, especially if you're unfamiliar with AI training. And then this one is a vision model that's fed into an autonomous vehicle track, and then you can put distractors in the way and see it move around the different objects in the road. So these are all examples that you can try on VibeSim, and then you can play around with the other stuff that's on the site. To do this though, you got to create an EDU account. Our company offers an account for non-commercial users that's free. It's just for all learners. You get access to Falcon Editor, which is on the left. You can see how it looks kind of like Unreal. You get access to all the digital twin library. And so things like the drones, four-wheel vehicles, they're already rigged and set up with controls. And also the sensor suites are already created that you can use. And so you can kind of assemble everything and start generating data. I have some examples you can follow to get started and start learning how to incorporate it all. I also do Kaggle competitions where you can generate data and try and beat the other people, win some money. So all that's free if you sign up for the EDU account. So the QR codes, I'll just leave this up while I'm answering questions. On the left, you can scan it and enter in your email on your phone, and then you'll have to validate it in your email. And then the site you can't view on your phone, but you can view it on your computer. You can just create the account, validate it. And then once you've created an account, if you want to get access to VibeSim, that's the other QR code. It's a form right now. So fill out the form, tell me you're interested. I will email you this week or next week, depending on how many people are interested in this, just to make sure we have enough servers, and then tell you how to log in and access all of that. So that is the end of my presentation. We got a couple minutes for questions, and I don't mind going over, but I know you guys have stuff to do and other classes to go to. So any other questions we have? Thank you guys so far. You've been super engaging.
Questions?
We got them all out in the middle, huh?
I have one more.
Yes, keep going.
So
Buy
from
more.
what you showed in the video, it's actually from the perspective of the ground, cameras.
Yes.
What if you have a camera on top of the drone,
Mhm.
capture this? Do you have data set like that, or the testing data set you have is all from the ground best observers?
For the VibeSim environment or for just the
For
general
your
data
testing,
set?
asking for you have this
On the cloud?
real testing that those are mostly
Oh,
from the ground, right? Also, telling that you can create technically you can create any from any perspective.
Yes, so we can create from any perspective. They could, I'm not sure what the data set, I think the data set is from the ground detecting into the sky, the real world one. And I think that might be more, I don't know what the use case was. I wasn't working with this customer. But I mean, we definitely could. We have capture sensors from the drones, and I'm not sure if they're doing them in real world. Does that answer your question? Yeah. There's definitely a lot of again, variability and flexibility that can be built in. And just because we haven't done it yet doesn't mean we couldn't or won't. Yeah. Any other questions? Yes.
I was just curious to know, has there been any development on multimodal models, like using camera, EO sensors, IR sensors together, fused as one picture, and then developing a sort of a model that can use these three sensors, fuse the information, and then give you an output?
I know that for this project, we did use IR. Felipe, how do we navigate using the multi-sensor modality for, let's say, one scenario to detect an object? Like if you had like 3 sensors looking for a drone and it detects it.
Yeah, we didn't do multimodal for this. I think definitely like we can make the data set and then the model building I think is kind of separately, and we can definitely just ensemble the different models with different modalities, or you can kind of create one multimodal model generally. But we for the most part did one modality at a time.
Are you familiar with ensemble learning?
Yeah, I mean, combining different models together and getting
Right. So I think maybe if you train the ensemble with the different sensors and then feed the data through, then you can get the, so instead of combining images, you're kind of almost having the 3 models talking to each other to decide what's best. I think that's what you were saying, right?
Yeah, so that's one option. You can do that, or you can just build one model that that rules them all, kind of.
We're trained on the different sensor modalities.
Yeah,
that's an interesting question though, kind of the matrix of the overlap of all of them, not just them as individually connected.
So like sensor fusion sort of thing.
Yeah.
So you get a better picture, because cameras might not do as well with long range objects. Radars might not pick up the pixels, and then you have lidars for the actual 3D detection.
Yes.
Sort of fusion.
Yeah, and I thought of that for like separate images. If you have all the sensors, then that one might detect it, but not as like an overlap of an image that creates more rich, complex data based on that.
Yeah, and I think that kind of thinking
Okay.
is yeah, I was just gonna say that kind of thinking is kind of one of the nice things for synthetic data, because I think traditionally it's just too expensive to do multimodal. Like you don't know if you can't really ask for more sensors without proving that what kind of benefit you get. So with synthetic data, you can kind of come back and be like, okay, if we have multimodals, this leads to X improvement, and then you can kind of support the argument for purchasing more modalities.
You should do it for a grad project.
Yeah.
Yeah, test it out, see what works best. That would be really interesting. If you guys want to do use Falcon for any grad projects or classes or anything, feel free to reach out to us. Definitely interested in getting into more EDU spaces. That's what I'm here for. So let us know.
Thank you.
Okay.
Thank you
great.
guys. Thank you for coming.
Second speaker.